Okay, so 3.7 is about linearization and differentials. And I'll bet you I am not sharing the correct screen. Can you guys see my screen? Like, can you see the notes? No. Nope. All right, just a second. I think when like everything went down this morning, it's like, I feel like everything is just messed up on my computer. All right, so I'm sharing my screen. Here we go. Yeah, I'm sharing my screen with you guys, but my airtime is not showing up. Window. Window to share. Okay, that is very small. That is way too small on my airtime, which is on my TV. So hold on a second here. Let me fix this. Okay, so 3.7 is linearization. And so what you're doing is you are using the tangent line to a curve to approximate certain values of the curve, okay? So y'all should like be taking notes on this right now and have paper out and pencil or something, because this is important. So you're gonna use the tangent line, and if the curve is concave down, your tangent line is gonna end up above your curve. And if your curve is concave up, then your tangent line is gonna end up below the curve. So for instance, this curve right here, does everybody see that like right here, all of this is a cube root curve, by the way. All of this part of the curve is concave down. So your tangent line, since it's concave down, whenever you have like something curved like this, the only way you can draw a tangent line is to draw the tangent line above it, right? It's never going to be below it, otherwise it won't be a tangent line anymore. It'll be like a secant line. So since the tangent lines are always above a concave down curve, the tangent are going to create approximations that are greater than, okay, the actual curve, because the tangent line is going to be above the actual curve. So therefore, all the y values on the tangent line are going to be higher than the y values of the actual curve. So if I draw my, draw my tangent line in here, my tangent line is above my curve, so my y values on my tangent line are going to be higher than my y values on the actual curve. So this is going to be an approximation for the curve that it'll be greater than the curve. So that's also known as an over approximation, right? If it's bigger, it's an over approximation. Now, when the tangent is to a concave up part, like just this little part right here of the curve, if I extend it a little bit, over here, the curve is concave up, right? Concave up like a cup. And so if I were to draw the tangent line down here, well, tangent to something concave up is always going to be below the curve. Like if you have like a parabola and you try to draw tangent lines to the parabola, the tangent lines will always be below the parabola. If the tangent lines were up here, they wouldn't be tangent lines anymore. They would be secant lines. So the tangent line, when your curve is concave up, is going to be an approximation for the curve, but it's going to be less than, because since it's below the curve, the y values that the tangent line give you are going to be lower than the y values of the actual curve. So they will be less than, or it'll give you an under approximation. Okay? Yeah.
Is there a question about this? Yeah, this is the college board assignment. I didn't know
this could have been, yes, but if you do the second derivative test, you can still come up with this result, because if you have a minimum, then your tangent would be below your concave up curve, which would give you an under approximation. So it was something alluding to this, but like you didn't have to use this directly, okay? We can always go over that AP Classroom assignment also, for sure. Yeah, that was Friday's work. Not everybody's turned that in yet. So as soon as we all get it done, we'll go over it for sure. Okay, so this linearization is to help you come up with approximations for like things that you would never maybe know in your head. And they're pretty accurate approximations. And you're going to use calculus and tangent lines to do it. For instance, in this first example, we are talking about how we can approximate the cube root of 70 without using a calculator. Okay, we're going to use calculus and we're going to use what we know about tangent lines. So this is what you do. You're given the cube root of something. For this example, it happens to be the cube root of 70. Okay, so this is not exclusive to just cube roots. This is anything, okay? He just picked a cube root because like we don't know very many cube roots, and especially we don't know cube roots of things that are not perfect cubes. So we're gonna be able to estimate this answer to like 2 decimal places of accuracy without using a calculator, which is pretty remarkable, okay, if you think about it. I mean, going out like a couple of decimal places accuracy, that's pretty good for a cube root. So what you want to do is you want to first find the closest perfect cube to 70. Okay, that's where this 64 comes from. Okay, it says centered at 64, and a lot of people when I go over this are like, well, why'd they pick 64? I mean, why didn't they pick 50? Why did they pick 100 or something like that? Why 64? Well, it's because 64 is the closest perfect cube to 70. So it doesn't have to be less than, it could have been greater than 70. You just want the one that's the closest, okay? Your perfect cubes are like 8 is a perfect cube, 27 is a perfect cube, 64 is a perfect cube. What else can you take the cube root of and it come out? Yeah, 125 is a perfect cube. So the one closest to 70 is 64. Okay, so that's why we picked that one. All right, now you are going to approximate this cube root of 7 using a secant line approximation, using 64 and x equaling 125. All right, so let me see what's on here. Yeah, so what you want to do is you want to define, all right, so that was first. So then you want to define the function. Okay, so the function for this particular example is not the cube root of 70. That's an actual value that we're trying to like figure out. The function itself is taking the cube root of a number. So the function for this is going to be f of x equals cube root of x. Okay. All right. So in order to approximate the cube root of 70, we need to come up with the equation of the tangent line at 70 that will give us the y value close to the curve. So like 70, if you look at this, here's your cube root function. 70 is right here. The tangent line that's closest, well, the tangent line that hits at 70 has a perfect cube right at 64. So if I could estimate the tangent at 64, I could get an approximation for the tangent line at 70. Like they'd be super close to each other, okay? Which would then give me a y value that would be super close to the cube root of 70, okay? So your goal is to come up with a tangent line that is really close to the value that you're looking for. Well, to get the tangent line, we're going to use 64, okay? But first, we have to write our tangent line in Taylor form. Like we've got to fill in all these little blanks and actually get an equation to the tangent line, okay? So in order to do the tangent line, we need a slope. Well, that slope is going to become the derivative of the function, okay? And then this x1 and this y1 are going to be the perfect cube. So this would be x equals 64. And if x equals 64, if I put a 64 in right here, what would be the y value? 4, right, the cube root. So x1 is 64 and y1 is 4. Okay. So the whole goal here is to estimate the cube root of 70 without using a calculator and to have it be very accurate. At least we'll have 2 decimal places accuracy. So what do we do first? We find the perfect cube closest to 70 and we define the function. Okay. If we were trying to find the square root of 70, our function would be the square root of x. If I was trying to find like the natural log of 70, my function would be natural log of x. Now we're going to come up with a tangent line that's really close to that value, and we're going to use the perfect cube for the x and the y1. Why aren't we using the 70 for the x1 and the y1? Well, if I was using the 70 right here, I'd have to put the 70 into my equation and find the cube root of that. Well, I don't know what the cube root of that is. That's what we're trying to figure out. So that's why we have to use something close that we do know the answer to, okay? All righty, so the derivative y'all can probably do in your sleep. So if f of x equals the cube root of x, you could write it as x to the 1/3, right? What would be the derivative of that? So that would be 1 like this. Now, we are using an x value of 64, so that means you need to put a 64 in for your derivative also. So this will be 1/3 cube root of 64 squared. Now, yeah, we can still do this without a calculator. Don't do the squared part first. It doesn't matter which one of these things you do first. You could do the cube root and then square it, okay? So whenever you have big numbers underneath a radical, take the root of it first and then raise it to an exponent, because these things, it doesn't matter which one we do first. So the cube root of 64 is 4. 4 squared is 16. So this becomes 1/3 times 16, which is 1/48. Okay? So your tangent line is y equals 1/48 times x minus 64 plus 4. Okay. So this equation right here represents this line, this pink line right here. That's the equation of that line. Y equals 1 over 48, x minus 64 plus 4. Okay? Once again, the reason we used 64 was because it was the closest perfect cube to the value that we're actually looking for. I have to be able to put something in here that I know will work out to be a whole number to help me with the tangent line. And the closer, the better. The closer I am to the value I'm actually looking for, the more accurate my approximation will be. All right, so this is the last step. This is where the magic comes from. You're gonna actually figure out the cube root of 70, but you're gonna use the tangent line to help you do that. So you're gonna plug 70 in for x. So y equals 1 over 48, 70 minus 64 plus 4. And you should be able to do this in your head. So this is gonna be 6, right? 6 over 48. What is 6 over 48 in lowest terms? 1/8 plus 4. Now, we could still do this in our heads, right? Because we could get common denominator. So the common denominator is going to have to be 8. So if this is 8, this becomes, thank you, 32 over 8. So y equals 33 over 8, right? 33 over 8, which if you wanted to make that back into like a decimal, that would be 4 point what? 33 divided by 8. Trying not to use a calculator. So that would be 432 back to 1/8, right? So 8 goes into 10 once, 2, so 1, 2, 16, right? 40. Remember long division? There you go. 4.125. I should have known that. 1/8 is the same as 1.125. So 4.125. So the square root of 70, I'm sorry, not square root, the cube root of 70 should be extremely close to 4.125. Okay. If we get our Desmos out, let me see if I can drag Desmos over. Okay. And if you put Desmos in, cube root is 70, 4.121. So we were off by 4/1000ths of a unit. Not bad. Not bad for doing that all with just a tangent line. Okay. So that's what this section is all about. We are going to approximate things that maybe you wouldn't normally be able to do mentally. We're going to use calculus and tangent lines to find those approximations. Also, notice that the actual, you guys at home, do you see my Desmos screen or no?
Yeah, we do.
All right, thanks, Jaden. All right, thanks, Bobby, Katie, awesome. I'm just making sure because like everything has been so like jacked up at school this morning that I don't know if my computer's actually doing what I think it is. All right, so anyway, so 4.121, that's the actual cube root of 70. Our approximation was a little bit bigger, right? Ours was 4.125. Remember what I said about the tangent line? When the curve is concave down, which it is at 70, this is concave down, your tangent line is going to be above the curve. So when you get your approximations, they will be over approximations, which is exactly what happened to us. We got 4.125. The actual is 4.121, but we're pretty darn close. I mean, considering like I didn't use the calculator, you know, we didn't use the calculator till the very end when we were checking it. So that's the goal for 3.7, okay? Now you don't have to do square roots or cube roots. We can also do other functions. Like we can do, well, we're gonna do a fourth root, okay? So in example number 2, we are looking for the fourth root of 17. So find the fourth root of 17. So what you want to do first is find the closest perfect, I don't know, what would we call this? Perfect fourth? Perfect fourth to 17. So what would be the number that is like when you take the fourth root of it comes out to be a whole number? Yeah, 16, very good. So that's going to be x equals 16, okay? Because the fourth root of, what is the fourth root of 16? 2, good, all right. So this becomes your x1 and this 2 becomes your y1. All right, second step, define the function. Okay, you define the function based on what you're being asked to calculate. You're trying to calculate the fourth root of 17. So your function is the fourth root of x. You basically just replace it with an x. All right, now the last step is to create the tangent line. So tangent line, y equals m times x minus x sub 1 plus y sub 1. You got your x sub 1 and your y sub 1 already. So this is going to be x minus 16 plus 2. Okay. The m, we're going to need to do a little bit of work for. So the m comes from the derivative. So if f of x equals the fourth root of x, you could rewrite that as x to the 1/4. What would be the derivative? Yeah, so that would be the 4th x cubed. Good, thank you. So that's going to be like subtract 1 from 1/4. That's how we got this, which would be a negative 3/4, and then put it back in the denominator. All right, you're going to evaluate this at x equals 16. Don't forget, you're going to use that perfect fourth and plug it into your derivative so that you can actually get a numerical value for the slope. So this would be, let's see, 1/4 times the fourth root of 16 cubed. Definitely don't want to do 16 cubed. So instead, do the fourth root part first, then cube it. So the fourth root of 16, we know that's 2. 2 cubed is 8. So this becomes 1/4 times 8, which is 32. So your slope is 1/32. Okay? All right, so you are now going to actually figure out the fourth root of 17. So you're going to do y equals 1/32 times 17 minus 16 plus 2. Well, 17 minus 16 is 1. So this would be 1/32 plus 2. So it'd be, oh goodness, what is the decimal for 1/32? What is the decimal? So 1/8 is 0.125. I gotta do the long division because I can't remember. I never have those things memorized. So that would be like 1 divided by 32. So 3 times 2 is 6. So that's 96. 4, 3, 32, 83. It's 0.0, so it must be 0.03125. It always ends in like a 125. So this is 2.03125. Okay. All right, so let's actually check it and see how accurate we are with this. Let me get my Desmos and plug that in. All right, so we had 2.03125. The fourth root of, how do I do fourth root? Fourth? Need my little, here we go. Nope. Where's, oh, I know what I could do. I go over here. Miscellaneous, that's what I want. But I don't want that. All right, so fourth root of 17. 2.0305. So look how close we were. 2.0305, 2.03125. So notice our answer is an over approximation. It's bigger, which means that the fourth root of x should be concave down. And if we kind of cheat and look at it, fourth root of x, yeah, and it is. Fourth root of x just looks like that. Kind of just looks like a square root, only a little bit higher, a little bit different. So fourth root of 17 would be way out here, somewhere out here. And it would be roughly 2.031 according to Desmos. Our answer was just a little bit bigger because the tangent line would be above the curve. Okay. Okay, the next example is not a root. It is instead, it's like an exponential. So 3 to the 5th power, well, this one's 3.01 to the 5th power. So we're going to figure this one out. So the first step to this one is to find the closest number to 3.01. Well, the closest thing that we know to raise to the 5th power is just going to be 3, right? We can figure out 3 to the 5th power. So x1 is 3. y1 is going to be whatever 3 raised to the 5th power actually is. So help me out with that. What would be 3 to the 5th power? Yeah, 243. So that's your y1. Your x1 is 3. Second step, define the function. Well, your function is that you're trying to find something, a decimal, raised to the 5th power. So your function is going to be x raised to the 5th power. third step is to now create a tangent line that's going to allow you to do this approximation and be like pretty accurate at it. All right, so y equals m times x minus x sub 1 plus y sub 1. Your x1 and your y1 are the 3 and the 243. So this will be x minus 3 plus 243. The m, we need to do some work. So the m is going to be the derivative evaluated at x equals 3. So if f of x is x to the 5th power, everybody, what would be the derivative?
Five x to the 4th.
Yep, thank you. And then we're going to evaluate that at x equals 3. So, yeah, somebody do that in their head. 3 to the 4th times 5.
$405.
Yeah, good. So 405. So 405 goes in here for the slope. So you're looking at this and you're like, I don't know, these are getting big, but that's okay. Remember, now you're going to actually figure out what you needed to find in the very beginning, which was 3.01 to the 5th power. So put 3.01 into your tangent line. So y equals 405 times, not a whole lot of space, 3.01 minus 3 plus 243. Well, I know 3.01 minus 3, that's just 0.01. So 405 times 0.01 minus 243. When I multiply any number by 0.01, what does it do to that number? Yeah, it divides it by 100, moves the decimal point over, right? That's really all that happens. And since there's 2 decimal places right here, the 0, 1, you're going to move the decimal point over in 405 2 spots to the left. So this will become 4.05 plus, this should be a plus right here, plus 243. So what is 4.05 plus 243? Well, that's not too bad. 247, like you're adding money, right? So that'd be 247.05. So 3.01 raised to the 5th power should be about 247.05. Let's actually check it out. .01 raised to the 5th power. Very close. 247.0770915. But I mean, like, we're very close. Super close. Notice our answer is smaller than the actual answer. Our tangent line approximation is less than or under the actual curve. And that's because the curve x to the 5th, and I am so like zoomed in that we can't even see it now. X to the 5th at 3, remember we're like super close to 3, which means I'm gonna have to go like way up here. But at 3, zooming out is just going to make it worse. It's not going to make it wonderful. But either way, at 3, you're on the right-hand side of the y-axis. And so your graph is going to be concave up. And since your graph is concave up, your tangent line, I suppose I could put that in. I wonder how good of a, I wonder how that would look. 405 parentheses x minus 3 plus 243. Yeah, it basically looks like a vertical line. That's just a crazy steep slope. Okay, but either way, this tangent line is going to be underneath the curve. It's going to be concave up, so the tangent line will be underneath, which means it will be less. Okay. Example 4. Let's keep moving so that way we get as many examples done as possible today. Then you can ask some questions on your other stuff. Okay, example 4. Approximate the natural log of e to the 10th plus 5. Determine if the linearization is an over or under approximation. All right, so you are being asked to find the natural log of this thing. Okay. Your first thing that you need to do is to find the closest natural log of something to the natural log of e to the 10th plus 5. So what would be the thing that we could take the natural log of, like in our heads mentally, easily, that would be really close to e to the 10th plus 5? So like E is like 2.72, something like that. When you raise that to the 10th power, that gets gigantic really fast. So when you add 5 to that, it doesn't really do much to that number, okay? So what would be a number that would be really close to e to the 10th plus 5, that we actually could do the natural log of it and it work out to be like a nice whole number? What could I put in here that I could like totally just do it in like 2 seconds and get a whole number? And it would be really close to this number.
E to the 10th.
Yeah, e to the 10th, sure. So the closest thing would be just e to the 10th. And what is the natural log of e to the 10th? 10, yeah, these things cancel each other out. So let's make sure that we define stuff correctly. The x value is what you're putting in here, okay? That's the x1 value. So that's going to be the e to the 10th part. And then the y value is what you get when you simplify this, when you put the e to the 10th in. So these go and you just get 10. That's properties of logarithms. That's going to end up being your y1. All right, good. Now, your second step is to define the function. Okay, so your function is, you're taking the natural log of something. That's what you're doing, okay? So it's the natural log of x. Okay. Yeah, you have e in there and all that good stuff. That's true. But don't forget, e is just a number, okay? E is just a number like pi. So you're taking, really the function is you're taking the natural log of something. All right, and we definitely don't have very many natural logs memorized. We only have one really, and that's the natural log of 1. We know that's 0. Everything else is like, I don't know. I don't know what the natural log of that is. So now we're going to do the tangent line. So this will be y equals m times x minus x sub 1 plus y sub 1 I've got the x sub 1 and the y sub 1 already. Remember, your x sub 1 is the e to the 10th. The y sub 1 is just 10, because that was what we got when we plugged that in. Okay? To get the slope, we need to take the derivative at x equals e to the 10th. So if f of x is natural log of x, what is the derivative of that? 1 over x, yeah. So if you evaluate that at x equals e to the 10th, this becomes 1 over e to the 10th. Okay? We put that in right here as your slope. All right, so I'm going to go on to an actual piece of paper because there's no way I'm going to be able to squeeze this all in. I don't think anyway. I probably could if I really tried, but I'm not going to. So your tangent line, remember, this is now going to help you figure out what the natural log of e to the 10th plus 5 is going to be. So it'll be y equals 1 over e to the 10th. So for the x, that's where you put the e to the 10th plus 5 part. E to the 10th plus 5. And then minus e to the 10th plus 10. Okay, so this step right here, sub in e to the 10th plus 5. All right, so what happens here and here? Cancel. You're left with 5 over e to the 10th plus 10. Okay. Now this one, I mean, you got e's and all kinds of stuff. So this one is like not as easy to do mentally. Definitely not. The other ones are, but once you get into like logarithms and stuff, you're going to need a little bit of help with your calculator. So if I actually plug that in, what does that give us? 5 over, let's see here. Okay, so 5 over e to the 10th power plus 10. So it's basically 10. 1, 2, 3, 2, 2, 6, 9, 9, 9, 6. Okay. And then if we check ourselves, just curious, like actually use Desmos to do the work, what's natural log of e to the 10th plus 5? Well, pretty close. I mean, like our tangent line, our like little calculus with our little derivative and all that good stuff did some good work for us. Because look how close, you guys. The tangent line and the actual are like, they're, let's see, 1, 2, 3, 4, 5, 6, 7. That's like 10 millionths or some crazy like amount of accuracy there. 100 millions? So it would be tens, hundreds, thousands, 10,000s, 100,000s, millions. Yeah, 10 millions accuracy. So not too bad for a little derivative and a little Taylor form. Not too bad. Okay. Any questions so far? It's the same process over and over to do this. You are finding a value closest to what you have that will work out really nice. Like mentally you can do it and get a whole number for the answer. And then you define the function, take the derivative and make a tangent line, and then sub in at the end and get your answer. So, okay, so that's called linearization. There's a couple more examples that deal with differentials. And this is the last part of the notes for 3.7. Remember what we're doing here when we take derivatives? You're finding the rate of change of a curve. So you're finding like how fast the y values on the curve are changing in relation to the x values. So Leibniz used this notation, dy over dx, change in y over the change in x. And so when you're using a straight line, your change in y over your change in x are like concrete terms. Like it's like this many units up, this many units to the side. That's your slope, right? But when you approach a distance, so like this x plus delta x, as this gets smaller and smaller and smaller, as this approaches 0, as that distance gets closer and closer and closer, and we approach that tangent line, then we can't just say like delta x, because delta x is an actual countable distance away. Instead, we use what they call a differential, which is where dx comes from, okay? In the beginning, we were like dx, like delta, but really it's called a differential because that distance away from the original x value is getting smaller and smaller and smaller so that this line can get more and more tangent instead of being a secant line. So this is to get you ready for next semester, really, because we're going to start talking about integration when you come back from break. And so in order to do integrals, you need to be able to undo derivatives. They're called antiderivatives. An integral is an antiderivative. It undoes the derivative. And so to do that, we need to separate this. This is called a differential equation, okay? You need to separate it so that the dy is all by itself, okay? So to do that, you treat this dy over dx just like a fraction, because that's really what it is. It's just a fraction, change in y over change in x. So to get that dy by itself, you're multiplying both sides. Like you're multiplying this side and you're multiplying by this side by dx. Over here, they cancel out. And then over here, it just ends up on the right-hand side. Okay, so these are differential equations that we are going to need to know how to use so that we can do our integrals next semester. So in example number 5, you're being asked to find the derivative of each function in differential form. So this is how you do it, okay? So we're going to do the derivative of this. So that would be dy over dt, right? Because the variable that we've got is a t. That's why it's a t in the bottom. What's going to be the derivative of 2t cubed plus 5t squared minus 3t plus 1? Yeah. Now, right now, this is a derivative like you're used to. Nothing's changed here. We're going to write this as a differential. Okay? Differential form means that you solve for dy. That's all that means. Okay? So we're going to multiply by dt on both sides. When you multiply this side, make sure you put some parentheses around it. So that goes. And now it's in differential form. Okay? You're just going to solve for the dy. Okay. So for this one, letter B, you're going to take the derivative of this. So this is going to be dz dx because your variable in this one is x. So let's take the derivative of this. Be super careful. You got x and you have a sine function. So product rule. This is u and this is v. So u prime, 3x squared, times v, sine 3x, plus v prime. Well, you got chain rule there, right? So this is going to be derivative of sine is cosine 3x times 3 times u, which is x cubed. That's the derivative. In differential form, you get the dz by itself by multiplying by dx on both sides. Okay? I'm just gonna just do that. Oh, I should put parentheses around this. There we go. That's better. Letter C, take the derivative. So this is dm dq. dq. Go for some dq. So now this is an exponential. Take the derivative of the exponential. So this is a way to like get you to review those derivatives, right? We did a little bit of everything in this one. So the derivative of e to the 5xq squared plus 1 is e to the 5q squared plus 1 times the derivative of the exponent, which is 10q. Okay. So there's your derivative. Now write it as a differential. So this would be dm equals e to the 5q squared plus 1 times 10q times dq. Okay. Notice that it's always the same variable on the right-hand side. Do you see that? Like it always ends up that they're all the same variable. This is all the same variable, even the dx. This is all the same variable. That should happen every single time. If you end up with something different, that means you got to go back and check your notation. Something's off. Okay, last example, example 6. A machined spherical bearing was measured with a caliper. Okay, calipers like those things, like those clamp things where like you're trying to measure and a bearing is round. Okay, so you're trying to measure the bearing. Okay, the bearing's radius was found to be 2.3 inches with a possible error no greater than 1/10,000th inches. What is the maximum possible error in the volume of the spherical bearing if we use this measurement for the radius? So picture this, you got a factory, they're cranking out these bearings, right? You got to make sure that they're accurately produced. Otherwise, they could do some major damage to an engine, okay? So they allow them to have an error when they come out of the factory of no more than 1/10,000th of an inch. If they have more than that error, they got to throw them out, do it over again, okay? So what's the maximum possible error in the volume if the radius is off by that amount? How much does that throw the volume off of the bearing? So what are we trying to do here? Maximum possible error in the volume. We need a volume formula. And it's of a spherical bearing. Volume of a sphere is 4/3 pi r cubed. Did anybody remember that? Did anybody know that? You're all so honest. Okay, that's cool. Well, now you got it, all right? So now we're trying to find the maximum possible error. So what we need to do is find the maximum of this volume. To find the maximum of this volume, we need to take the derivative of it. So this would be dv dr. Okay? Change in volume over change in radius. The derivative of this, what would be the derivative of this? Yeah, 4 pi r squared, which incidentally is the surface area of a sphere. Like if you take the derivative of the volume, you end up with the surface area of the sphere, which I thought was pretty cool. Now you know. All right, so the change in the volume over the change in the radius is equal to this, 4 pi r squared. I want to know what the maximum possible error in the volume would be. So really, I want to know how much is the volume going to change. So I need to solve for dV. This represents change in volume. This represents the change in the radius. I'm trying to figure out the change in the volume. So I want to get dV by itself. So dV equals 4 pi r squared times dr. Multiply by dr on both sides to get change in volume all by itself. All right, now plug in everything that you know. We know, well, 4 pi is just a number. We know that r should be 2.3 inches. So this would be 2.3 right here, squared. dr. What's dr? Yeah, dr is how much the radius is allowed to vary. So it's the change in the radius, no greater than 10 thousandths of an inch. So you put that in for dr. That's where that actually goes. Okay? So this would be 4 pi, 2.3 squared. You're not having to do this mentally. We are going to use Desmos for this. So 4 times pi times 2.3 squared times 0.1231. So this comes out to be, I'm getting 0.006647. That's plenty of decimal places. Actually, if we wanted to stop there, I guess I would say 4.8. And this is change in volume. So this would be inches cubed. So if you allow the radius to have no greater than 1/10,000th of an inch in change, like if you allow that change, it's going to throw the volume off by 6,648 millionths of a cubic inch, which doesn't seem very much, but if you're dealing with like an airplane or a large, anything like large that would have a lot of impact with the volume being thrown off, then you got to make sure you're accurate. So there you go. That's example 6. That's it for the 3.7 notes. I was hoping I could get through that a little faster for you, but at least we finished.